The exponential function. Welcome back. To begin, let us recall our previous discussion where we observed that exponential functions exhibit a significantly faster rate of growth compared to polynomial functions. Building on that observation, in this subsection, we are going to formally define what an exponential function is. We will also analyze its key mathematical properties and examine how it behaves when plotted on a graph. Definition of the exponential function. Now that we have established that exponential functions grow much faster than polynomial ones, let's move on to the formal definition. Simply put, an exponential function is a function where the variable x appears in the exponent rather than as the base. To define this mathematically, we use a constant base, b, with the condition that b must be greater than 0 and not equal to 1. Under these conditions, the exponential function is defined as f of x equals b to the power of x. In this expression, the constant b is called the base, and x is the exponent or the power. It is important to remember that x can be any real number, whether it is positive, negative, or 0. To make this more concrete, let's look at an example. If we choose the base b to be 2, the function becomes f of x equals 2 to the power of x. In this specific case, as x increases, the value of f of x doubles for every unit increase in x. This doubling effect is exactly why these functions exhibit such rapid growth. Now that we have a clear definition of the exponential function, we will proceed to examine its fundamental characteristics, such as its domain and range. Fundamental characteristics. Now that we have formally defined the exponential function, we want to move from the basic definition to a deeper analysis of how it actually behaves. To truly understand the nature of the function f of x equals b to the power of x, we will examine three critical areas: its domain, its range, and its overall graphical properties. This will provide us with a comprehensive understanding of how the function operates before we look at real-world applications. Domain. Now that we have defined the exponential function, let's begin analyzing its fundamental characteristics, starting with the domain. First, as a refresher, the domain of a function is simply the set of all possible input values, represented by x, for which the function is mathematically defined. When we apply this to our exponential function, b raised to the power of x, we have to ask ourselves if there are any restrictions on what x can be. In this case, there are none. We can plug in any real number as the exponent, whether that number is positive, negative, or 0. Because of this, we formally state that the domain is the set of all real numbers, which is denoted by the symbol r, or written in interval notation as open parenthesis negative infinity, comma, positive infinity, close parenthesis. Now that we have established what values we can put into the function, let's move forward to the next slide to see what values we can expect to get out of it, which is known as the range. Range. Now that we have established the domain, let us move on to the range. As a reminder, the range represents the set of all possible output values, which we typically denote as y. To understand the range, think back to our definition of the exponential function. We specified that the base, b, must be a positive number. Because the base is positive, raising it to any power, regardless of whether the exponent is positive, negative, or 0, will always result in a positive value. Consequently, the output of this function can never be 0, nor can it ever be a negative number. Therefore, we conclude that the range is the set of all positive real numbers. In mathematical interval notation, this is written as the open interval from 0 to infinity. The key point. Now that we have established the domain and range of our function, let's focus on a critical characteristic that helps us plot the graph. First, it is important to remember a fundamental rule of exponents. Regardless of the value of the base, b, provided that b is greater than 0, any number raised to the power of 0 is always equal to 1. Because b to the power of 0 equals 1, this tells us something very specific about the geometry of our function. It means that the graph of the function, f of x equals b to the power of x, will always pass through the point 0, 1. This point serves as a consistent anchor for every exponential function we encounter, and it will be very useful as we move forward to analyze the overall behavior and the growth of the graph in the next few slides. Behavior of the function. Now that we have established the key point at 0, 1, let's examine the overall behavior of the function. Because we have specified that the base, b, is greater than 1, you will notice that as the value of x increases, the value of b to the power of x also increases. In mathematical terms, we describe this as an ever-increasing or monotonically increasing function, meaning the graph consistently climbs as you move from left to right. To put this more formally, as x approaches infinity, the function f of x also approaches infinity. Essentially, the larger the input becomes, the larger the output grows, and it does so at an accelerating rate. This sets the stage for our next discussion, where we will see what happens to the graph as x moves in the opposite direction toward negative infinity. The asymptote. Now that we have discussed how the function grows as x increases, let's examine what happens in the opposite direction. As x becomes a very large negative number, the value of b to the power of x becomes a very small positive fraction. To help you visualize this, let's look at a specific example. If we set our base b to 2 and our exponent x to -10, then 2 to the power of -10 is equal to 1 divided by 2 to the power of 10. This results in 1 over 10^24, which is a value incredibly close to 0. When we plot this on a graph, you will see that the curve approaches the x-axis, which is the line where y equals 0, but it never actually touches or crosses it. Because the graph gets infinitely close to this line without ever reaching it, we call the x-axis a horizontal asymptote. This is a crucial characteristic of the exponential function that we will keep in mind as we move toward our real-world examples in the next slide. Real-world example, population growth. Now that we have analyzed the theoretical properties and the graphical behavior of the exponential function, let us apply these concepts to a real-world scenario. Exponential functions are frequently used to model populations that grow at a constant percentage rate, which is a perfect example of the rapid growth we observed in the previous slides. Consider this scenario. Suppose we have a colony of bacteria that doubles every hour, starting with an initial population of 100 bacteria. To translate this into a mathematical model, we will follow a step-by-step breakdown. First, we must identify the base. Since the population doubles, our base, b, is equal to 2. Second, we define our variable. In this context, let x represent the time elapsed in hours. Third, we formulate the equation. The population, p, as a function of x, is given by p of x equals 100 multiplied by 2 raised to the power of x here. 100 represents our starting point, and 2 raised to the power of x represents the doubling effect over time. Finally, let us calculate the population for x equals 3, meaning after 3 hours have passed. We begin by substituting 3 for x into the equation, which gives us p of 3 equals 100 times 2 cubed. First, we calculate the power. 2 cubed is 8. Then, we multiply this result by the initial amount. 100 times 8 equals 800. Therefore, after 3 hours, the population has grown to 800 bacteria. This example illustrates how the function increases quickly as x grows, which leads us perfectly into our final summary and a look at some common pitfalls to avoid. Key takeaways. Now that we have seen how these functions apply to real-world scenarios like population growth, let us consolidate everything we have learned into a final summary. First, let's review the general form. The exponential function is written as f of x equals b to the power of x, where the base, b, must be greater than 0 and cannot be equal to 1. Moving on to the domain, as we established earlier, you can plug any real number into the exponent. Therefore, the domain is all real numbers, stretching from negative infinity to positive infinity. Next, consider the range. Because a positive base raised to any power will always yield a positive result, the range consists of all positive real numbers, written as the interval from 0 to positive infinity. A key graphical feature to remember is the intercept. Regardless of the base, any number raised to the power of 0 is 1, which means the graph will always pass through the point 0, 1. In terms of growth, since we are focusing on a base greater than 1, the function is strictly increasing. This means that as x increases, the value of the function grows at an accelerating rate. Finally, let's recall the asymptote. As x becomes more negative, the graph approaches but never touches the x-axis. Thus, the x-axis, or the line y equals 0, serves as the horizontal asymptote. Please keep these fundamental properties in mind, as they will be crucial in helping you avoid the common mistakes we will discuss in the next slide. Common mistakes. Now that we have covered the fundamental properties and a real-world application, let us conclude by discussing some common mistakes students often make when dealing with exponential functions. Avoiding these pitfalls will ensure you have a solid grasp of the concept. First, it is very common to confuse the exponential function, b to the power of x, with a power function, x to the power of b. While they look similar, they are fundamentally different. In an exponential function, the base is a constant value and the exponent is the variable that changes. In contrast, in a power function, the base is the variable and the exponent remains constant. These two types of functions have entirely different growth rates and mathematical properties, so be sure to identify which part of the expression is the variable. Second, let's revisit the range. A frequent error is stating that the range is y is greater than or equal to 0. However, as we discussed when analyzing the horizontal asymptote, the graph approaches the x-axis but never actually touches or crosses it. There is no real value of x that you can plug into the function to make b to the power of x equal to 0. Therefore, the range is strictly y is greater than 0. Finally, be careful when handling negative exponents. Some beginners mistakenly assume that if the input x is a negative number, the resulting output y must also be negative. This is incorrect. Remember that b to the power of negative x is equal to 1 over b to the power of x in mathematics. A negative exponent indicates a reciprocal, not a negative value. Since our base b is always positive, the output will always remain positive, regardless of whether the exponent is positive or negative.